So for example number 9, now we're going to do the reverse now. So in this case we're given a power series in sigma representation, and we're going to figure out what's the function that it's represented. Well, so number 1, every time we have a series like this, well, try to find like something that looks familiar from, you know, from one of the known series. For example, here in this case, what I notice here is this 2n factorial. And you might wonder where would that come from? Well, so looking at the series for the series table right here, the one that has a 2n factorial is the one with cosine. Also, that cosine has a -1 to the n and a u to the 2n. So let's see how is that similar or different from that. Well, number 1, the alternating factor differs by the power n plus 1 as opposed to just n. Sorry, and the power of x, it's for n and not 2n. So there's a couple of things that we might want to do first. So number 1, so that's a sigma n equals 0 to infinity. I'm going to write this as -1 to the n times -1 to the first power. And this x to the 4n, this is the same as x to the 2 times 2n. The whole thing divided by 2n factorial. And sigma n equals 0 to infinity. This -1 to the n, the -1 to the first, it's going to be a negative number, a negative sign that I'm just going to write outside. And this will be -1 to the n. And on top of that, well, I'm going to rewrite this x to the 2 times 2n. I'm going to write it as x squared quantity to the 2n over 2n factorial. So, but in this case, well, if we write this as in the following form, sigma negative sigma n equals 0 to infinity, -1 to the n, u to the 2n over 2n factorial. Well, in this case, you can think of the u to be x squared. That means then that's going to be negative oh, no more sigma notation, because -1 to the n, u to the 2n is over 2n factorial. That's cosine of u, which in this case is negative cosine of x squared. And well, in this case, so this is the function that is being represented. So that means in this case, well, that's a function there. All right, so let's see what's next. So oh, for the interval of convergence, of course, IOC, interval of convergence. Well, for the cosine function in this case is all real numbers. And even so, because we have this x squared, well, that x squared you can plug in everything. So no issue with it. For letter B, sigma k equals 0 to infinity of v to the -kx. Well, so be careful in this case, because this is combining the exponential function, and no, this is not going to be an exponential function. Well, it will include, but it's not going to be just that. So I'm going to rewrite the series like sigma k equals 0 to infinity, and I'm going to rewrite this as e to the -x to the k power, because power of another power multiply the powers, and I'm going to leave the k outside. And in this case, this will have the form of k equals 0 to infinity. All right, and that's going to be u to the k, where in this case the u will be e to the -x. This means then that this is going to look like 1 over 1 minus u, where the u is e to the negative x. Alright, and that's the function being represented by this power series. Now let's think about the radius of convergence, or rather the interval of convergence. So what we need to do is recall that for the geometric, the interval of convergence, IOC for short, it's when the absolute value of u is less than 1. That is, when e to the negative x, or the absolute value of e to the negative x is less than 1. That means when e to the negative x less than 1 and greater than negative 1. Alright, but now when we want to solve for x over here, well, here we have trouble because we would have to take ln on the three sides of the inequality. And well, what happens when you take ln of negative 1? Well, for now, the natural log of a negative number is not defined, as opposed to ln of 1, which is 0. So in this case, well, because in this case there are no restrictions for this power series, because actually the domain of the exponential function, it's all real numbers. Okay, let me rearrange this. Let's move on to one more. So we have sigma 3 to the n equals 0 to infinity of 3 to the n x to the 4n plus 2. Alright, so one thing that you might want to do is break up all the powers. And well, so let's see. I'm going to pull. So for this one, whoops, no, I didn't need to do this. So we will rewrite this x to the 4n plus 2 as sigma n equals 0 to infinity 3 to the n x to the 4n times x squared. And of course, keep in mind that our power series are usually in terms of n and not in terms of x. So what I'm going to do is I'm going to take this x squared outside of the sigma series, and I'm going to leave together 3 to the n x to the 4n. All right. Now, in this case, one thing that you might want to consider is notice how the power of n is common to both factors 3 and the 3 and the 4. All right. So in this case, well, I'm going to rewrite this as sigma, or rather x squared, sigma n equals 0 to infinity. That's 3x to the 4th power to the n power. And well, this looks like I'm going to write this with u equals 3x to the 4th, or rather, okay, I'm going to write here x squared 0 to infinity, and that's u to the n, and that's x squared 1 over 1 minus u, and simply just recall that u equals to 3x to the 4th. All right, so that's x squared over, or times rather, 1 over 1 minus 3x to the 4th. And simplifying this, that's just going to give us, okay, that's x squared over 1 minus 3x to the 4th. All right. So that's the function represented by this power series. Now let's talk about the IOC, that is the interval of convergence. So again, in this case, for the geometric form, we're going to have u, the absolute value of u, less than 1, which in this case it's the absolute value of 3x to the 4th power less than 1. Well, checking the absolute value of that quantity, well, we really don't need that. So that's 3x to the 4th less than 1, x to the 4th power less than 1/3. And then when we take the 4th root right here, be careful, because that for even roots, for even indices, that's going to be, well, x less than, or absolute value, the 4th root of 1/3, which in this case is, well, breaking up the absolute value inequality. That's less than the 4th root of 1/3 and greater than negative the 4th root of 1/3. Or in interval notation, 4 root of negative 4 root of 1/3 to 4 root of 1/3. Of course, if you want to rationalize the denominators, that's fine, but it's not necessary. Alright, so let's have a look at other problems. So like evaluating integrals that we wouldn't be able to otherwise evaluate without power series. So let's evaluate the integrals below. So what we're going to do here is use power series, because, well, try to use U substitution, well, it's not going to work, or, well, partial fraction or any of the methods, simply not going to work. So we're going to represent these functions in terms of power series in the following way. So let's find the integral of, okay, so let me rewrite this, because this looks like 1/1 sort of minus u. Well, so what if we write this integral as 1/1 minus negative x to the 7th with respect to x times the integral of 1/1 minus u, and in this case, well, think of the u to be the negative x to the 7th power. So that's the integral from, well, in this case we're ready to write this in sigma notation. N equals 0 to infinity u to the n with respect x. Okay, so now let's go back and substitute the u. That's the integral sigma n equals 0 to infinity of u, which is negative x to the 7 to the n power with respect to x. And let's simplify this a little bit. Recall that the negative 1 to the n is going to turn this into an alternating series. X to the 7n dx. And, well, to integrate this series, all you have to do is focus on the x to the n, in this case x to the 7n. So this will be, well, if we integrate, this will be c plus the series sigma n equals 0 to infinity of negative 1 to the n to times x to the 7n plus 1 over 7n plus 1. That's simply general power rule. All right. In a similar way, we're going to evaluate this integral of x to the 6th cosine of x squared. I think you could even do integration by parts. I mean, like 6 times. But why bother? I mean, I don't think it's still a feasible task. I mean, so we're going to use, in this case, power series instead. So what are we going to have? That's the integral x to the 6th. And that's, I'm going to write this cosine of u with respect to x, where the u equals x squared. So that's the integral of x to the 6th power, that sigma n equals 0 to infinity for the power series of cosine, which is negative 1 to the n, u to the 2n over 2n, the whole thing factorial. All right, and that with respect to x. So let's go back for substitute for u. So that will be the integral of x to the 6th sigma n equals 0 to infinity and that's negative 1 to the n u, which is x squared to the 2n over 2n factorial with respect to x. So before integrating, we are going to simplify the series, introduce this x to the 6th factor inside of the sigma series, and then we will integrate. So that's the integral of x to the 6th, sigma n equals 0 to infinity. That's 2 times 2, and that's going to become negative 1 to the n, x to the 4n over 2n factorial with respect to x. That's the integral. Well, now we may be able to introduce the powers of x. So x to the 4n plus 6, because same basis, which is x, add the exponents. And that's a negative 1 to the n, x to the 4n plus 6 with respect to x. So all we have to do is integrate x to the 4n plus 6, add 1 to the exponent to get c plus sigma n equals 0 to infinity, negative 1 to the n, x to the 4n plus 7, add 1 to the exponent, divide by that new exponent, that's 4n plus 7 times 2n factorial. And this is final answer. That's the integral of x to the 6th cosine of x squared using power series. And this is the end of this section.